Hi class, welcome to chapter 5, the lipids. The lipids include triglycerides, phospholipids, and sterols. So what exactly are lipids? A lot of times we say that lipids are fats, but they actually include more than fats. So they include the triglycerides, which are made up of fats and oils, phospholipids, which help support cell membranes, and sterols. And they also include the fat-soluble vitamins. So we're going to talk about all these things coming up. We're actually going to highlight the fat-soluble vitamins in their own chapter later on in the semester. All right. So what three elements make up carbohydrates? Hopefully you remember that they are carbon, hydrogen, and oxygen. And those three same elements actually make up fats. So carbohydrates and fats have similar chemical composition, just the carbons, the hydrogens, and oxygens in fats are arranged in a different way than they are in carbohydrates. Fats tend to have many more carbons and hydrogens because on each carbon there's at least 2 hydrogens. And so because of that, they send more electrons into the electron transport chain, which is something we're going to talk about a little later on, and they can produce more energy or more calories. So fats have over twice as many calories as carbohydrates do, and they come in at 9 calories per gram. Triglycerides. Triglycerides are the chief form of fat in the diet, and they're actually the chief form of fat in our bodies as well. So when we eat foods, the type of fat we primarily eat is called a triglyceride. And the name kind of explains what it is. It's tri, meaning 3, glyceride. So there is one molecule of glycerol with 3 fatty acids. That is a triglyceride, and we're going to see some pictures of that coming up. A monoglyceride is 1 fatty acid and a glycerol, and a diglyceride is 2 fatty acids and a glycerol. It is possible to have mono or diglycerides in food, but triglycerides are more common. Also, when we consume triglycerides, our body can break them down into di or monoglycerides. So what is this glycerol backbone that I'm talking about? Glycerol is a very simple molecule. It has 3 carbons, it has 3 oxygens and multiple hydrogens, and it serves as kind of the foundation for where the fatty acids are going to bind. And glycerol, it has an OL at the end of it, and so glycerol is actually a type of alcohol. Fatty acid. So remember, in a triglyceride, we have a glycerol and 3 fatty acids. And a fatty acid is simply a long chain of carbons, and at one end of the chain there is a hydrogen, which indicates a methyl group. So we have carbon, 3 hydrogens, and at the other end of the chain, which is indicated in pink, there's an acid group or carboxylic acid, and that is the carbon with the double bond to the oxygen and the single bond to the oxygen and the hydrogen. So a fatty acid has a methyl group and a carboxylic acid group and has many carbons in between those. Most fatty acids in our diet have 18 carbons, but it's possible for them to be different lengths. Generally speaking, fatty acids include only even numbers, so you could have 4 carbon, 6 carbon, 8 carbon, etc. And they can be classified based on their size. You could have short chain fatty acids, medium chain fatty acids, long chain fatty acids. But like I said earlier, most of them contain 18 carbons. So these are some examples of foods that we eat. So animal fats generally have 18 carbons, and those are considered to be saturated fats. We're going to talk about the difference between saturated, monounsaturated, polyunsaturated fats coming up. Olive and canola oil also have 18 fats. Sunflower, safflower, corn, flaxseed, and walnut also have 18 carbons in their fatty acid chains. Chemical structure diagrams. So how do we draw these fats? What we're indicating here is bonds. So each time you see one of these single lines between a molecule, it indicates a single bond. So a carbon and a hydrogen bound together, carbon and carbon bound together. And in this format, this is the long way of writing out bonds. Because people don't want to spend the time writing every C and every H, what they do instead is these kind of mountain-shaped curves. And at the peak or trough of every mountain, it's assumed that there is a carbon. So each peak really represents a carbon. And it's also assumed that coming off of each peak, there is a hydrogen. It's just not drawn in because drawing these lines takes a long time, as you can see. So sometimes you'll see chemical structures as indicated at the top. Other times you're going to see them as indicated at the bottom, and you're going to make the assumption that each one of these peaks or troughs is a carbon with two hydrogens attached to it. When you see something like this, two lines, that represents a double bond. So there's two bonds between the carbon and the oxygen. It's also possible to have three bonds, not between a carbon and an oxygen, but we don't see those a lot with our fatty acids. So I'm going to clear all this drawing and then attempt to go to the next screen, which once in a while my little device will freeze and not allow me to do that. So I think it will now allow me to do that. All right. Saturated fatty acid. So a saturated fatty acid is a fatty acid where on every single carbon there are 4 bonds. So remember that these lines represent bonds, and on every single carbon, there are 4 lines. So some of them have lines to other carbons, hydrogens. This one has 2 lines to an oxygen, 1 line to an oxygen, 1 line to a carbon. And it means that all the spaces for bonds are totally full, especially between the carbons. So between the carbons, you're only going to see single bonds in saturated fatty acids. So only single lines between the carbons. And you'll have 2 hydrogens or more on each carbon. The carbons are saturated, meaning they're full of hydrogen. Unsaturated. In an unsaturated fat, you're going to see a double bond in between the carbons. And so the double bond is represented here. And so what you can see is a double bond here and a double bond here. When there is one double bond, we say mono because mono means one. And when there are 2 or more double bonds, we say poly because poly means many or more than one. So unsaturated fatty acids, see this says unsaturated. Unsaturated means that there are not hydrogens every single place there could be. The bonds of this molecule are not full of hydrogens. Instead, you have carbon-carbon double bonds. So the presence of double bonds indicates that a fat is unsaturated. And when a fat is unsaturated, it actually has different properties, both chemically, from a culinary standpoint, and in our body from a health standpoint. So if you've heard about saturated fat versus unsaturated fat before, really what that's referring to is the chemical structure and the bonds between the carbon groups. So let's see if this will allow me to close this presentation. Okay, so point of unsaturation. The point of unsaturation is the place where the very first double bond occurs. So if we actually go back to this slide, you could count how many carbons before the first double bond. So in the bottom picture, you have 1, 2, 3, 4, 5, 6 carbons before you see the first double bond. And so this bottom fatty acid is actually what's called an omega-6 fatty acid. So the point of unsaturation occurs at the 6th carbon, and so we call it an omega-6 fatty acid. So an omega-3 fatty acid would have the very first double bond on the 3rd carbon. And like I showed you in the last slide, the omega-6 fatty acid would have its first double bond at the 6th carbon. So I'm sure many of you have heard of omega-3 fatty acids and maybe omega-6 fatty acids, and now you know that what that's actually referring to is the place where the double bond is. And so here is a picture of that. So in the omega-3, you see we have this first carbon, which is the methyl carbon, the green one, and we count 1, 2, 3. You see a double bond. In the bottom diagram, we have the first carbon. We count 1, 2, 3, 4, 5, 6, and that's where you see the first double bond. So the top fatty acid is an omega-3 fatty acid, and the second fatty acid is an omega-6 fatty acid. And the placement of these bonds, just like the fact that some fats have double bonds and some do not, affects chemical properties, health properties, and many different features. So omega-6 fatty acids behave differently and have different functions in our body than omega-3s, and it's simply because of the place where the double bond is. So we've kind of reviewed some types of fatty acids as well as glycerol, and now we're going to talk a little bit about breaking down fatty acids, etc. So the breakdown and formation of fatty acids is actually very similar to carbohydrates. And I guess I should say the breakdown and formation of triglycerides is very similar to carbohydrates. So when you create a disaccharide, what is the reaction called? A disaccharide is a sugar, right? So it's 2 sugars combined. So when you combine 2 single sugars, you have a condensation reaction. How do you think you create a triglyceride? Remember, when you're going to create a triglyceride, you're going to combine 3 fatty acids and a glycerol backbone. That is also called a condensation reaction. So I have a picture of that right here. So in a condensation reaction to create a triglyceride, you're going to have your glycerol backbone, which is indicated in this kind of orange color, and it is going to combine with 3 triglycerides. In this particular picture, the triglycerides are all different, the fatty acids. It's going to combine with 3 fatty acids. So in this particular picture, each fatty acid is different, and they can be the same or different. And in a condensation reaction, remember, it's like water condensing on a glass, and water is lost. So in blue here, it shows which ions are going to be removed from each part of these chemicals, and it's 2 hydrogens and oxygen. So water is going to be formed when you make a triglyceride from glycerol backbone and 3 fatty acids. Going back to the degree of unsaturation. The degree of unsaturation is how many double bonds are in a fatty acid. So if a fatty acid has 0 double bonds, it's considered saturated. If a fatty acid has multiple double bonds, it's considered unsaturated. And the more double bonds a fatty acid has, the more unsaturated the fat is. So they have different characteristics depending on the double bonds. Saturated fats and fats with very few double bonds tend to be more solid at room temperature. Fats with multiple double bonds tend to be more liquid at room temperature. And so if you think about oils versus butter versus lard, you can think about which might be saturated and which might not. Oxidation is when oxygen combines with a molecule, and in the case of fats, the oxygen usually breaks one of the double bonds to sneak in, and so that can actually cause the fats to turn rancid. I don't know if you've ever smelled a rancid fat or not, but it means spoiled. It's very off-smelling. And so fats that have more double bonds or are unsaturated, such as a polyunsaturated fat, is at higher risk of being oxidized because there are more places for that oxygen to sneak in. These are some pictures comparing a saturated fat on the left, so there are no double bonds between the carbons in this saturated fat, and then a unsaturated fat on the right. So on the right, you see that there are double bonds between the carbon, and what you can see with these pictures is that the double bonds actually change the entire shape of the triglyceride. So a saturated fat has a very straight shape, and because of that straight shape, it packs very neatly in organized fashion, and so it forms hard fats. The unsaturated fat has a very kinked shape or a curvy shape, and that curvy shape does not allow it to form a cohesive structure, and because of that, it's liquid. When we talk about foods, sometimes people will say, oh, that's a saturated fat. Oh, that has lots of unsaturated fat. And that can be true, but in reality, most foods actually have multiple types of fat, and we refer to them based on their predominant fat. So coconut oil, for example, is mostly saturated fat. Saturated fat is indicated here by red. If you've ever gotten a jar of coconut oil, you know that it's solid at room temperature and then it melts once you heat it up. Butter is also solid at room temperature. Beef fat is generally pretty solid. Palm oil, lard, and chicken fat. If you think of the fat on the chicken versus the chicken fat, while it is saturated, it also has a high proportion of monounsaturated fats. So chicken fat is not as hard or dense as beef fat. You then have the different oils, and you can see they're generally a mix between monounsaturated fats and polyunsaturated fats. The greener ones indicate omega-6. The yellow ones indicate omega-3. So at the very bottom, you can see that there's not very many oils that are high in omega-3s, but some that are high include flax and fish oils, such as salmon. All of the other oils are much higher in omega-6s. Olive oil, however, is not necessarily that high in omega-6, so olive oil can be a pretty good choice along with fish oils. Hydrogenation. So hydrogenation is the process of adding hydrogens across the double bonds between carbons to break those double bonds and form single bonds. So if you remember, a fat with a lot of double bonds is going to be more liquid, but a fat with single bonds is going to be more solid. And so also, a fat with double bonds is more likely to become rancid or oxidized because the oxygen has a place to interrupt those double bonds, where a fat with single bonds is not easily oxidized because there's no place for the oxygen to sneak in. So, the food industry created a chemical process called hydrogenation. And hydrogenation is where they add hydrogen ions to unsaturated fats to make them saturated. And so they can make a liquid fat more solid at room temperature, depending on how many hydrogens they add. One byproduct of hydrogenation is something called a trans fat. And trans fats have many negative health consequences. So what exactly is a trans fat? A trans fat is a name given to a fat that has a double bond and has hydrogens on opposite sides of those double bonds. So the hydrogens on the double bond are across from one another, and that allows the shape of this entire trans fat to actually be very straight. So remember, other fats that are straight are saturated fats. So to our body, trans fats look just like saturated fats, and they're going to be more solid at room temperature. The opposite of a trans fat is, sorry, the drawer is out of control, is a cis fat. And with a cis fat, the hydrogens are on the same side. And because they're on the same side, it gives this fat kind of a mountain or peak shaped or a upside down V shape. And remember, the kinked shape causes molecules to be stacked unevenly, and that can cause them to be more liquid at room temperature. So, I have so much trouble with this drawing tool. Okay, phospholipid. A phospholipid is another type of lipid. So we talked about triglycerides, and now we will talk about phospholipids. Phospholipids are similar to triglycerides, but they have a phosphate group, so that kind of refers to their name, and they also have a choline group. And triglycerides are only soluble in water, triglycerides are only soluble in fat, and they don't like water, but phospholipids are soluble in both water and fat. This is an example picture of a triglyceride, and at the bottom of this, you can see it has a P and 2 oxygens. That's the phosphate, part of the phosphate group. And then it has a group with a nitrogen in it, and that part comes from the choline. And it has a positive charge on the nitrogen and a negative charge on the oxygen. And those 2 charges on this molecule allow it to interact with water. So if you learn anything about water, maybe from a past chemistry class, you'll learn that water has a slight dipole charge. So charged molecules can interact with water, where uncharged molecules, like the fatty acids on the top of this phospholipid, do not. So phospholipids are unique in that they can interact with both water and fat, and because of that, they serve important roles in cell membranes. So in foods, they can help emulsify fat, meaning bring fat into liquid. So an example of a fat that is not emulsified is oil and water, or you could also do oil and vinegar, say if you're making a homemade salad dressing. If you just add oil to water or oil to vinegar, the oil will float on the top and it won't evenly mix. If you sometimes buy a salad dressing in the store, you can buy salad dressings that have emulsifiers, and you can also buy salad dressings that do not have emulsifiers. But one that I've seen that does have an emulsifier is Wishbone Italian. And I know it has an emulsifier because I can't see the levels of oil and water separated. They're all mixed together. So salad dressings are just one example where they add a phospholipid to help mix the oil and the water together so that it all comes out kind of evenly. Natural phospholipids are found in eggs, soybeans, and peanuts. And then in the body, they serve as cell membranes and also emulsifiers. Sterols. So sterols are another class of lipids, and these are compounds, well, here they are, like cholesterol, and they have 4 kind of ring-shaped figures. They are only from, so cholesterol specifically only comes from animal foods, and there are other plant-based sterols, but cholesterol only comes from animal foods. And this would be like meat, eggs, fish, poultry, dairy. A hormone slash vitamin that looks a lot like cholesterol is actually vitamin D. So we have a precursor to vitamin D in our skin that is a type of cholesterol, and when activated by UV rays, we can convert that to vitamin D. What roles do these sterols play in the body? So remember, sterols are compounds that have these 4 rings, and sterols act as bile acids, which we're going to talk about what bile does, but bile is a very important, it's an emulsifier, and it's something that our liver produces, and it helps us break down fats. They can be the precursors to hormones such as testosterone, cortisol, and vitamin D. And then we can get plant sterols. Plant sterols do not come from animals. Regular cholesterol does. Plant sterols look like cholesterol to our body. So when we consume plant sterols, we actually can excrete more regular cholesterol, and this can lower our total cholesterol levels. And then cholesterol also helps with cell membranes. So cholesterol is an important part of our cell membranes that allows them to be kind of fluid and mobile and plastic or elastic. Okay, quick review. So a triglyceride is made of, hopefully you said 3 fatty acids and a glycerol. How many double bonds do the different fatty acids have? A saturated fat should have none. A monounsaturated fat, remember mono means 1, and poly means more than 1. So poly will have 2 or more. What are some sources of saturated fats? Remember that saturated fats primarily come from animal foods, but are also found in things like coconut oil, palm oil, lard, etc. Monounsaturated fats. So these were found primarily in olive oil, but also canola and peanut oil. And then trans fats. I said trans fats can be produced chemically, and so they used to be found in things like pie crust, pudding, chips, cookies, pies, margarine. However, generally speaking, in the United States, we've eliminated trans fats from food production via legislation, and so we don't find them as much in commercial products. They do actually occur naturally in animal products like meat and dairy. However, it seems that the ones that occur naturally are not as harmful as the ones that were being produced by chemical processes. All right, so how do we break down these fats once they get into our body? Going back to chapter 3 on the digestive system, maybe you remember that there was something called the gallbladder, there was bile, there were different enzymes and hormones that were released. We have our mouth, all sorts of different components of the digestive tract. And maybe you watched the video on the lymphatic system and remembered that the lymphatic system was used to transport fats. So hopefully you remember those things, but we'll review just in case. So fat digestion in the GI tract. When we eat fats, they start in our mouth, and we don't have a lot of fat digestion or absorption in our mouth, but our mouth is warm, it's body temperature, and that can help to melt fats that potentially were solid. So if you put butter in your mouth, it's going to melt, etc. So this can help break down some of the saturated fats potentially. We also have a very, very small amount of gastric lipase in our stomach. So once fats get to our stomach, we have a very, very small amount of an enzyme that can break them down. Next, fats will travel to our small intestine, and the top part of our small intestine is the duodenum. And remember that once that acidic chyme hits the small intestine, it signals the release of different hormones and enzymes. And one of those will be CCK, or cholecystokinin. Cholecystokinin will trigger the gallbladder to contract, meaning squeeze, and the gallbladder is the place where we store bile. So remember that bile is produced by the liver and stored in the gallbladder. Next, we'll have pancreatic juices secreted, and pancreatic juices include bicarbonate as well as lipases. And lipase is an enzyme because it has the ACE on it, and it breaks down lipids. So that can help break down triglycerides into monoglycerides, fatty acids. Most of the absorption and digestion of fats will occur in the small intestine. Very little will occur in the large intestine. So remember we talked about emulsifiers and emulsifiers being able to kind of intermix with water and fat. And fats only like fats, and our enzymes in our body actually like water. So if we didn't have emulsifiers, we would not be able to have enzymes mix with fats, and we would not be able to digest. So certain emulsifiers, such as bile, allow fats to mix with water and then allow their exposure to enzymes and their subsequent breakdown. Hydrophobic or hydrophilic. So something that is phobic, a phobia, like arachnophobia, is a fear. So phobia is a fear, and hydro refers to water. So something that is hydrophobic fears water. And fat fears water. Fat loves fat, and it fears water. Hydrophilic means loving water. And so water loves water, and enzymes love water. But fat does not love water. So fat is hydrophobic. Emulsifiers, we can make them from cholesterol, and emulsifiers, so we make them from cholesterol. Cholesterol is the base for bile. Bile acts as an emulsifier to take large pieces of fat, break them off into much smaller pieces, and then surround them with bile, which has a charge, and bile can interact with both the fatty component of the triglyceride and the water. And so bile allows fat to go from this floating top layer, like in the salad dressing, to intermixed. And once the fat is intermixed into the bloodstream, it can mix with enzymes, and enzymes can bind to the fat to break it down. There is something called enterohepatic circulation, and this has to do with intestine. Enterocytes are intestinal cells, and hepatic refers to the liver. So it's kind of the cycle between the intestine and the liver, and it's the cycle of bile. So bile is made by the liver. It's stored in the gallbladder. Once the gallbladder contracts, the bile is secreted into the small intestine. The bile binds the fats. Unfortunately, or fortunately, I guess fortunately, both, it's a plus and minus, but our body is very efficient, so we don't want to waste our bile because we had to make it. So what happens is the fats are generally transferred across the cell, and the bile is recycled. The bile goes back into the bloodstream and is taken back up by the liver so that the liver doesn't have to make it all from scratch again. The good thing about this is that we reserve our bile, so we don't have to make a lot. The bad thing about this is it also keeps our cholesterol a little bit higher because we use cholesterol to make bile. In the large intestine, however, it is possible to bind bile, and what can bind bile is soluble fiber. So soluble fiber can come from like pears or apples, different fruits and veggies, and whole grains. And soluble fiber can actually trap bile, and this will cause it to be excreted in the large intestine. And so bile will be removed from the system, and this will cause the liver to have to make more bile, and the liver uses cholesterol to make bile. So in that regards, when we eat fiber, it actually lowers our total cholesterol because we're using cholesterol to break down. We're using cholesterol to make new bile. All right, so some review. When you break a disaccharide, what do you have left? So remember, a disaccharide was a sugar. If you break it down, you're going to have two monosaccharides. We already talked about formation reactions. Formation reactions involved condensation, And the opposite of condensation is hydrolysis. How do you think triglycerides are broken down, and what do you have left? What would their reaction be called? So very similar type of reaction. We're going to have a hydrolysis reaction, and the hydrolysis reaction is going to be able to separate some of the fatty acids from that glycerol. So just like this, when you have a hydrolysis reaction, you're adding water. In a condensation reaction, you're producing water. But in a hydrolysis reaction, you're adding water. So water is represented as the HOH here. And if you add 2 waters, you can break 2 bonds, which is shown in this diagram. If you add 3 waters, you can break 3 of the bonds. So in this particular diagram, 2 water molecules were added, 2 of the fatty acids were separated, and you're left with 2 fatty acids and a monoglyceride. And that's called a hydrolysis reaction. Once you break down these fats, we can begin to absorb them. So there's different methods of absorption depending on the type of fat. Short chain fatty acids, which are pictured in this number 1, medium chain fatty acids, and glycerol, remember our glycerol backbone, those all can be absorbed directly across the enterocyte or the intestinal cell into the bloodstream. So short chain, medium chain, and glycerol can go directly into the bloodstream. Larger fats, however, as shown in number 2, cannot go directly into the bloodstream because remember, fats are hydrophobic and the blood is hydrophilic. So when we break down our fats, this is an example, we have a monoglyceride. That monoglyceride can be separated into individual fatty acids. Individual fatty acids can form what's called a micelle, and we're going to talk about a micelle or a micelle coming up. The micelle can then pass through the intestinal cell. It's repackaged into a triglyceride, and then the triglycerides are packaged into something called a chylomicron. And the chylomicron is a large particle that moves through the lymphatic system, which in this diagram is represented by the yellow. So large chain fatty acids have to be first made into micelles, next transported across the intestinal site, then packaged into chylomicrons, and then they can go through the lymphatic system. So let's get a closer look about micelles. Micelles are emulsified fat droplets. So remember that emulsifiers allow fats to mix with water, and so most of these contain bile, which is our emulsifier. Micelles can help bring fatty acids across the intestinal cell because they can mix with both fat and water. The hydrophobic tail is afraid of water, but the hydrophilic head loves water and can move across the cell. Once the micelle is transported across the intestinal cell, the fats are reconfigured into triglyceride, and then they're packaged into something called a lipoprotein. And a lipoprotein is like a fat taxi. A lipoprotein can move the fats through the bloodstream. And so there are 4 different types of lipoproteins, and we're going to talk about each type in more detail coming up, but the very first type you saw was a chylomicron, and chylomicrons primarily contain triglycerides, and they're the largest of the lipoproteins. Next, we have very low-density lipoproteins. We have low-density lipoproteins and HDL or high-density lipoprotein. So you may have heard of LDL and HDL as being quote-unquote cholesterol. And they're not actually cholesterol, they're lipoproteins that transport cholesterol. So we're going to talk about those coming up. So this diagram is comparing different types of lipoprotein. The largest purple molecule on the left is a chylomicron, which is the largest of the lipoproteins. And then this chart kind of on the right side of the screen represents what the components are of each lipoprotein. Triglyceride is represented by orange, and so chylomicrons contain the most triglycerides, and the least amount of protein. Because they have the most triglycerides and the least amount of protein, they're not very dense. Protein increases density, and fat or triglycerides do not. After a chylomicron, the next type of lipoprotein is a VLDL, which is represented in yellow on the left, the second column on the right. And VLDL stands for very low density lipoprotein, and it also contains primarily triglyceride, but has a higher percentage of phospholipid, cholesterol, and protein. So what happens between a chylomicron and a VLDL is the chylomicron will be circulating throughout the bloodstream and depositing a lot of its triglyceride particles to the cells. And after that, it will be a lot smaller, lower percentage of triglycerides. As VLDL travels through the bloodstream, more and more of those triglycerides will be picked up, and eventually the particle will form a LDL, or low-density lipoprotein, which has fewer triglycerides, a higher cholesterol content. So LDL is actually distributing cholesterol to the cells. And so that is one of the reasons LDL is considered the quote-unquote bad cholesterol. LDL is not a cholesterol at all. It's a lipoprotein, but it's primarily made up of cholesterol. And then HDL is the last and smallest and most dense of the lipoproteins, and it's made primarily of protein. And one of the roles that HDL does is scavenges the bloodstream for excess cholesterol and returns that cholesterol to the liver for recycling. And so HDL kind of clears up the excess cholesterol from the bloodstream, and in this way it protects the body. That's why HDL is considered the good cholesterol, even though really it's a lipoprotein. So in more detail, chylomicrons contain primarily triglycerides, and they're the largest of all of the particles, and they transfer these triglycerides to the bloodstream. VLDL also transports triglycerides as well as different fats to the body, and they give all their triglycerides to cells. After they have done this, they are converted to LDL, so that's what this diagram is showing. LDL comes from VLDL, and most of the triglycerides have been removed from the VLDL, so what's left is primarily cholesterol. And LDL will circulate through the body, making that cholesterol available to the cells and the tissues. It's possible that some of this cholesterol is not taken up by the cell and instead ends up kind of stuck in the bloodstream. And if that happens, that cholesterol is at risk for oxidation, can cause inflammation, form blood clots, and contribute to heart disease. So LDL in that sense is referred to as the bad cholesterol. HDL actually moves through the bloodstream and is represented in blue here. And what HDL will do is bind to cholesterol and bring it back to the liver for recycling. HDL is the most dense because it's composed primarily of protein. And this is considered the good cholesterol because it kind of cleans out the cholesterol from the bloodstream. It is considered the good cholesterol, but remember that HDL and LDL are actually both lipoproteins, not cholesterol. They're lipoproteins that have cholesterol in them. Okay, so the quote-unquote good and bad cholesterols. The bad is LDL. I think of LDL as being low or a loser, and the good is HDL. HDL is like hot or high or handy, it's good, or healthy. So HDL is good, LDL is bad. Because LDL is considered bad, we would want to lower our LDL, and we could do that by consuming mostly poly and monounsaturated fats, watching our weight, consuming soluble and insoluble fibers, different phytochemicals, moderate alcohol consumption, physical activity, limiting trans fats, etc. And then I asked this question, is fat in the body all bad? And the answer to this is no. Our body actually needs fats. Fats have many functions, and we're going to talk about those coming up. So fats are essential, and that's good news for all the people who love fatty foods and oily foods and greasy foods. And they're actually learning more and more about benefits of fat in the diet. So many of you may have heard of ketogenic diets. Ketogenic diets are higher fat diets, much higher, sometimes even up to 90% fat, but the general population usually does 60 to 80% fat. And they're actually finding some substantial health benefits of these high-fat diets, which is surprising considering what we've thought for the last 30 years was that fat was bad and fat caused you to be bad. But now we're learning that potentially it's more carbohydrates that are causing us to gain weight versus fat themselves. This is a super complicated picture of everything I just explained, and you do not have to memorize it, but I just put it here for you to see. But you should definitely know the difference between LDL, HDL, chylomicrons, VLDL, etc. So, cholesterol levels. General goals for blood cholesterol. If you were to go to a lab and have your blood levels analyzed for cholesterol, they look at your total cholesterol, which includes LDL, HDL, triglycerides, chylomicrons. They look at just the LDL particles, and they look at just the HDL, and they look at just the triglycerides. So generally speaking, it's healthier to have higher levels of HDL and lower levels of LDL. Roles of triglycerides. So remember, I said fats actually have many important functions, and some of them include providing energy, insulating the body, protecting vital organs, cushion from shock, helping us use carbs and proteins more efficiently. So if we have adequate fats, we can break down fats for fuel instead of having to break down muscle for fuel. There are essential fatty acids, omega-3s and omega-6s. We're going to talk about the functions and benefits of those. And fat cells actually secrete many hormones that are essential. So the essential fatty acids. The essential fatty acids include linoleic acid, which is an omega-6 fatty acid, and linolenic acid, which is an omega-3 fatty acid. And remember that the omega-6 and omega-3 have to do with the location of the double bonds in the fat. In general, the American diet is higher in omega-6 fatty acids because these come from a lot of vegetable oils, which we consume in high quantities. And we tend to be lower in omega-3 fatty acids. You can see the sources: flax, canola, walnut, wheat germ, soybean, nuts and seeds, vegetables, and also fish oils are high in omega-3s. From the omega-3 fatty acids, we can make something, or there are different types of omega-3s, such as EPA and DHA. And EPA is eicosapentaenoic acid, DHA is docosahexaenoic acid, and they both have different functions, as well as can be synthesized from linolenic acid. So DHA is important for growth, development, visual acuity, especially in infants, and cognitive development. So it's important for infant development. They often fortify infant formulas with this. You might see it advertised. More and more, they've been fortifying cow's milk with this. Omega-3 also plays a role in inflammation and reduces inflammation. And so by reducing inflammation, specifically within the arteries and the cells and just the entire body, it plays a role in reducing the risk of heart disease. Eicosanoids. So eicosanoids are things that are derivatives of fatty acids, and they act kind of like hormones, but they're a little bit different than hormones because they only affect the cells where they're produced or cells very close to them, where hormones can affect the entire body. And they also have different kind of cellular responses. Omega-3 derived eicosanoids can help lower blood pressure, prevent blood clots, increase vessel diameter, which is indirectly going to reduce blood pressure, decrease inflammation, and decrease cell growth. which as far as decreasing cell growth, primarily we're referring to like cancer cell growth, which would be bad. Omega-6s increase blood clotting, decrease vessel diameter, increase inflammation, and increase cell growth. So they have kind of opposite effects, and the ratios of omega-6s versus omega-3s are very important. If you have too many omega-6s versus omega-3s, you're going to have blood that clots a lot faster and easier, and blood clots can raise your risk of heart disease or stroke. Excess lipids. So our book says excess lipids cause weight gain. I like to highlight that any nutrient in excess can cause weight gain. And in fact, more and more they're actually learning about lipids and high-fat diets, primarily fat diets, as possibly a mechanism for weight loss. So any nutrient in excess can cause weight gain. Fats can contribute to heart disease, and high levels of circulating LDL can cause plaque buildup. Plaques are accumulation of fat, muscle, calcium, inflammatory processes that form on the inside of vessels, and they make them narrower. And when the vessels are narrower, it increases blood pressure. And if, say, a piece of this plaque breaks off or the blood begins to clot, it can occlude or block the blood vessel and lead to a heart attack or a stroke. So high levels of LDL can lead to heart attacks or stroke. Trans fats can contribute specifically to heart disease as well as certain cancers. They've shown that foods that tend to be higher in animal fat may contribute to colon cancer. And they don't necessarily cause cancer, but they can make it worse. Recommended intake of fat. So how much fat should you eat a day? The AMDR for fat is 20 to 35% of calories should be from fat, and saturated fat should be less than 10% of your calories. Cholesterol, this says less than 300, but they actually just recalled this recommendation. So currently there is no number on cholesterol. They've actually changed this to be something like consume a diet low in cholesterol or don't consume excess cholesterol, but they took away the number. So you should note that. And then, for example, how much fat would you be consuming if you had a 2,000 calorie diet where 30% of your calories came from fat? You guys will have some questions like this on your study guide. It would be 65 grams of fat, 20 grams saturated fat. And like I said, the recommendation for cholesterol actually went away. So, what kinds of foods are high in fats? Hopefully you can think of some. Whole dairy products like whole milk, ice cream, whole yogurt, butter, cuts of meat. Sometimes you can see the fat. Sometimes the fat is more difficult to see where it's marbled throughout the meat. Coconut, palm, donuts, cookies, nuts, seeds, etc. What kinds of foods are low in fats? So fruits, veggies, fat-free milk, fat-free dairy. If you are having meats with the fat trimmed, or lean cuts of meats or lean grinds of meats like low fat beef. Beans and legumes tend to be lower in fat, and the fats that they do have tend to be healthier. Soy tends to be lower in fat, etc. So both the amount of fat and the type of fat matter. It's not just, one or the other. It matters whether you're consuming saturated or unsaturated and how much. These are some example sources of the different types of fats. We saw a similar kind of explanation to this in that bar chart where it showed what types of foods had which type of fat as the predominant fat. And then this is a picture explaining or kind of depicting how simple dietary changes can cut down fat as well as calories. So pork chop, if you don't trim the fat, it has 19 grams total. If you do trim the fat, you can get rid of 10 grams of fat, and it now only has 9 grams of fat. You cut the calories by more than 100. Baked potato with butter and sour cream. 14 grams of fat. Baked potato without butter and sour cream, less than 1 gram of fat. Whole milk, 8 grams of fat. Fat-free milk, less than 1 gram of fat. You saw this picture already. Oh, no, you didn't. You saw similar ones. This is looking at omega-6s in red and omega-3s in green. Fish oil supplement. So fish oil, many people may take a fish oil supplement, and so how to read them can be important to know what you're actually getting. So on the front of this fish oil, it says 1,000 milligrams omega-3. But when you actually look at the back, it says that it only gives you 300 milligrams of EPA and DHA. So the other omega-3s in this particular product must be different ones. So although it has fish oil, it does not necessarily have 1,000 milligrams of just omega-3. It has only 300. So read the labels carefully. Also look at the serving size. Many serving sizes are for multiple pills a day. Okay, calculating daily goals for fat. If your energy intake was 1,800 calories and your goal is 30% of calories from fat, how many grams of fat should you eat each day? So what you're going to do here is you're going to do 1,800, and I know my pen and my drawing skills are not that good, and you're going to multiply it by 0.3 because that represents 30%, and you're going to get 540 calories from fat. So that's calories from fat. And then remember that in 540 calories, there are 9 calories per gram. So you're going to divide this by 9 calories per gram. And you are going to get 60 grams of fat. So if you were consuming 1,800 calories, 30% of your calories from fat, you would get 60 grams of fat per day. You can also do the next example. You should get 49 grams. So try the next example on your own and then check your work. All right. What percentage of the calories in a particular food come from fat? So if a cup of whole milk has 150 calories and 8 grams of fat, how many calories come from fat and what percent? So we know in each gram of fat, there's 9 calories. So we multiply 8 grams of fat by 9 calories. We get 72 calories total. Then we can take that 72 calories from fat and divide it by 150 calories in the milk. We get 0.48. To convert this to a percentage, we multiply by 100 and we get 48%. So in that glass of whole milk, there are 48% of the calories that come just from the fat. If you have low-fat milk, it has a lot less calories. So what we're going to do for low-fat milk is the same thing. We're going to say there are 3 grams of fat in low-fat milk, and there are 9 calories per gram. And so we're going to get 27 calories in this low-fat milk coming from fat. And then we're going to take 27 and we're going to divide that by 90 total calories. And we're going to get 0.3, and we multiply that by 100 to convert to the percent, and we get 30% of the calories from fat in this low-fat milk. So if you want to be consuming fewer of your calories from fat, you can pick low-fat products. Uh-oh, I'm back to this again. Okay. Fast food and high-fat foods. So remember we talked about the type of fat and the quality of fat and the amount of fat. So all of these foods pictured here are actually pretty high in fat, But all these foods pictured here have other fantastic nutrients like fiber, protein, phytochemicals, vitamins, and the type of fats that they have, monounsaturated in the olive oil and omega-3s, polyunsaturated, are all healthy fats that can help reduce heart disease, inflammation, and are considered essential for cognitive function and vision development. So the type of fat really matters. In order to eat more quote unquote healthy fats, you can do kind of these meal makeovers. So this particular meal is a steak with bacon, blue cheese, Italian dressing. And it's pretty high in saturated fat. So the purple is representing this meal on the left. If you wanted to change the fat profile to be lower in saturated fat and higher in unsaturated fat, you could switch the bacon and the cheese for sunflower seeds and avocado, and you could switch the steak for salmon, which is going to be higher in essential fatty acids. So there's ways to have similar meals but tweak the food so that you're getting some of the healthier, less inflammatory fats. All right, quiz. So saturated fatty acids are fully loaded with hydrogens. A triglyceride contains 3 fatty acids and a glycerol. The difference between cis and trans fatty acids is D, the configuration around the double bond. Which of the following is not true? Lecithin is it is not essential. So C, it is not essential. Chylomicrons are produced in the small intestine. Transport vehicles for lipids are called lipoproteins. The lipoprotein most associated with a high risk of heart disease is LDL. Which of the following is not true? Fats do not contain glucose. The essential fatty acids are D, linoleic and linolenic. A person consuming 2,200 calories a day who wants to meet the diet and health recommendations should limit fat to, did you guys do the math? It should be B, so 50 to 85. All right, that's the end. Thanks for listening.